Mr. Heffernan here, and here is a short video on centripetal motion using universal gravity to solve some more difficult problems. So here we have a good example of centripetal motion involving universal gravity. So here we have the planet Earth. It provides an action, force of gravity on the moon, which provides the centripetal motion or force necessary to keep the moon in its orbit, which is around 29.3 days. And 384,000 kilometers. And then it provides a reaction force on the Earth. So you'll see the Earth actually move around a little bit around itself while it's in orbit around the Sun. And it provides the tides. So that's why the ocean tides exist, thanks to the lunar gravity, the moon. So here's one first example question. We have an astronaut of mass 80 kilograms who weighs 784 newtons, or 176 pounds, when standing on the surface of the Earth. Now, the Earth's radius is 6,380 kilometers, and if you travel up to the space station, that could be approximately 1,250 kilometers in altitude or height, so from the surface. So if the astronaut does travel up there, what's the astronaut's new weight? So we're going to use the universal gravity formula for this. So we got universal constant of gravity, big G, 6.67 times 10 to the negative 11. We got the mass of the Earth, which is 5.98 times 10 to the 24. And we have the mass of the astronaut, which is 80 kilograms. Then we have the position of the astronaut. We're going to be the radius of the Earth, 6,380,000 meters, plus the altitude, 1,250,000 meters, and we're going to square that. So altogether, when we're done doing the math, we find the astronaut only weighs 548 newtons in orbit, or 123 pounds. Now, the astronaut, of course, being in orbit, falling around the planet, will feel like the astronaut doesn't have any weight. So the apparent weight is 0, but the actual attraction of gravity to the Earth is around 123 pounds. So an 80 kilo astronaut loses 53 pounds by going up 1,250 kilometers. So because you go from 176 pounds down to 123 pounds, that's a loss of 53 pounds. Okay, so here's another solution or another method of solving the problem. Instead of using the force of gravity, what we can do is use ratio and proportion math. So in this case here, the constant of the universe isn't going to change. The mass of the Earth is not going to change. And the mass of the astronaut is not going to change. You don't lose mass when you go into orbit. You don't lose any kilograms. You only lose pounds and newtons. So the only thing that matters is the position, r. So the force of gravity depends on 1 over r squared. So we're going to use a little ratio trick. If you want to compare a new force of gravity to an old one, so force of gravity 2 equals force of gravity 1, so we're going to compare these two, the new and the old. All you have to do is look at the fraction, and whatever you see in the original fraction, that's where the 2 is going to go, or the new situation. So if r is on the bottom, the denominator, then over here, r2 is on the bottom, or the denominator. And then the 1 does the inverse. So the inverse of the bottom is on the top, so r1 squared is on top. This is there's about 8 steps of math to show you how this works, or you can memorize the shortcut. Whatever the fraction is, that is where the 2 will go in the new fraction. Okay, so in this case here we have the old weight, 784 newtons. The old position, 6,380 kilometers. Don't even need to use meters. And we have 6,380 plus 1,250 kilometers. And when you work out the math, you get the exact same answer. So the advantage of using ratio and proportion ratio and proportion, is you don't have to actually know the mass of the planet. You don't have to memorize the universal constant for gravity. You don't even need to know the mass of the astronaut. You can solve this question. Okay, example 2. An alien on the surface of planet X weighs 1,000 newtons, where the radius is 5,000 kilometers. If the alien climbs a mountain, how high must it be to lose 2 newtons of weight? So we have an alien. We don't know the mass of the alien. We don't know the mass of the planet. All we know is the radius of the planet and the force of gravity. So in this equation, big M for the mass of the planet and little m, mass of the alien, we don't know these values. So there's not much we can do with this formula. But luckily for us, the only thing that does change is the force of gravity and the radius. And the force of gravity, once again, depends on 1 over the radius squared. So if we do the exact same ratio and proportion trick that I mentioned before, the R is on the bottom, so R2 is on the bottom, and that means R1 has to be on top. And so F, the force of gravity 2, equals the force of gravity 1, R1 squared over R2 squared. Fill it in. On the mountain, the alien will have 998 newtons of gravity pulling them down, where on the surface of the planet before, it was 1,000 newtons pulling them down. And the radius of the planet, we can call it the big R, X, for the radius of planet X. And on the bottom, it's going to be the radius of planet X plus the height squared. So what I'm going to do is cross multiply the 998 with the bracket. So I'm going to bring this bracket up and the 998 down. The 2 minus signs will eventually cancel out. And then when you square a bracket like this, a binomial, you're always going to get the 1 value squared, the other letter squared, and in the middle it's always going to be 2 times the first one times the second one. So now I've got h, which I'm looking for, h squared. I'm looking for h, and I have another value. And so what I'm going to do is going to bring this 1,000 over 998 over. And because it was negative, negative, that turns into a positive. Bring the positive over, turns into a negative. So now I'm going to have a 1rx squared, subtract this fraction rx squared, and I'm going to factor the rx squared out. And so I'm going to get this. So now if I'm using the quadratic formula, where x is equal to negative b plus minus the square root of b squared minus 4ac all over 2a, the coefficient a will be 1, coefficient for b will be 2, and the coefficient for c would be 1 subtract 1,000 over 998. And of course we've got, this is in the units of the planet's radius, rx. So I'll leave that as an exercise in math for you to try out yourself, but in the end we get the following answer. 0.001503 rx, okay, which is basically 0.15% the radius of the planet, or negative 2.001503 rx. So how does that work? So this is saying the height of the mountain right here is exactly 0.001503 times the radius of the planet. Or instead of going from the radius up, you can go down a radius, down a second radius, and then go up 0.001503. So that's why there's a minus 2 there. It's just basically saying you get the exact same answer on the opposite side of the planet. So now that we have this, we can plug in the radius of the planet, 5,000 kilometers, and we get an answer of 7.515 kilometers. So this mountain's not quite as tall as Everest, which is 8.82, but it's a pretty tall mountain. And this alien, if they weigh 1,000 newtons, they will lose 2 newtons of weight by climbing that mountain. Right? So this is great. We don't know the planet's mass, don't know the alien mass, and we can still do this question using ratio and proportion math. Okay, example 3. Okay, I call it 2 here, but it's actually 3. In this case here, we have two planets orbiting their respective stars. We have the planet Terra orbiting the planet OJ, and we have the planet Pelota orbiting the planet Hugo. Right? So, the planet Terra is 1 astronomical unit from its star OJ. 1 astronomical unit is the distance from the Earth to the Sun, which is 1.495 times 10 to the 11 meters, or 1 astronomical unit. And then we have Pelota. It's 80% further out, or 1.8 times further out than Terra is. It's at 1.88 so it's further out, so it should take longer to get around usually. But it's got a more massive star. The star Hugo is 3 times more massive than the star OJ. And so if Terra takes 400 days to get around, we want to know what is the time for the planet Pelota. All right, so we got our 2 star systems. Star system for Hugo, which has the planet Pelota, and the star system OJ, which has the planet Terra. So once again, we don't know a lot of information, but that's okay. We can use this ratio proportion math. So using Kepler's third law, the period squared of an orbit is equal to 4 pi squared over g for constant of gravity for the universe, mass of the star, times the radius of the average orbit cubed. So since we have a bunch of constants here, we're just going to ignore them and make a ratio and proportion out of them. So here's a proportionality statement. The period squared is proportional to the radius cubed over the mass of the star. So using that trick that I mentioned before, look at the fraction, whatever you see in the fraction, that's where the 2's are going to go. So if we want to compare the 2 periods, t2 squared to t1 squared, they're both squared because period is squared. Look at the fraction. Where is r? R is on the numerator, so r2 cubed is in the numerator. M is in the denominator, so m2 is in the denominator. And then the 1's do the opposite. If m2 is on the bottom, m1's on top. If r2 is on top, r1's on the bottom. And that's it. That's a real easy trick. It's pretty easy to do. And it skips 8 lines of math. Okay. So here we go. The period of 2 squared, or period of Pelota squared, would be the 400 days squared for Terra, times the mass of the star OJ, divided by the mass of Hugo, which is 3 masses of OJ. And then we have the R2, the new radius is 1.8 AU cubed over 1 AU cubed. So check this out. I'm not even using scientific units. There's no meters here. There's no kilograms. Everything cancels out. Mass of OJ over OJ. AU cubed over AU cubed cancels out. And the only thing left is days. That's awesome. So in the end, I get my answer, 557.7 days. And that's it. I can do a question like this even without knowing all the information. So Pelota has an orbital period which is of 557.7 days, where its radius is 80% further out, and its star has triple the mass of the star for the planet Terra. So in summary, universal gravity problems can be solved with equations or with proportionalities. And these are the equations we usually use for universal gravity. So here's the universal gravity formula. Big G, which is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. The mass of the big object, like the sun. Mass of the smaller object, like the star, like the Earth. And it's going to be towards the center of the star, okay, over the radius squared. And if you're using Kepler's third law, which is derived by using centripetal force equations and universal gravity, you get the period squared is equal to 4 pi squared over gm r cubed. And another little fun formula you can derive is the orbital speed is equal to gm over r square rooted. Now, if you are using ratio and proportion math, if you have an equation like x squared equals a constant or some constants, yz cubed over b root c, it's easy. You remove the constants, so the equal sign goes away and becomes proportionality. And then whatever you see for the fraction, that's where the 2's are going to go. So if you want to compare x2 to x1, x is squared, so it's x2 squared equals x1 squared. Where's the y and the z? They're on top, so y2, z2 are on top. Where's the b and the c? They're on the bottom, so b2 and c2 are on the bottom. And boom, you got it to work. So in class, I call this the Jedi Trick, just for fun. Okay, it looks like magic, even though it's not. It's just math. So I hope this helps. Thank you.